let's take a look at your homework from the 5-5 Review and Reinforcement, the 5-5 Practice Problems, and the Electron Configuration Quantum Numbers Review sheets that you had last night for homework. Please make sure that you edit your papers as we look at each of these. So for the first section, that was your true-false. So number 1 said the Pauli exclusion principle states that an orbital, remember an orbital, we represent that with the boxes, I call them the mailboxes, but this is like an s orbital. The orbital can hold a maximum of blank electrons, 2 electrons, and 2 is the word that's underlined, and that is true. Remember, if the underlined word is incorrect, you want to fix it and make this statement a true statement, but that was true. Number 2, the sum of the superscripts of an electron configuration represents the total number of neutrons in the atom. Well, it's called the electron configuration, not the neutron configuration. Therefore, that's a false statement, and you should put electrons in the place of neutrons, and that would make that a true statement. Number 3, the Aufbau principle states that electrons are added one at a time. It says here to the highest energy orbitals available until all the electrons of the atom have been accounted for. Well, that's a false statement. The underlined word here says highest. Well, Aufbau, remember, is a German word, and in German it means to build. And when you build something, you build from the foundation up. So you should change the underlined word highest to lowest, and then that would be true. You do fill your lowest orbitals up first, and then you continue filling up your orbitals until all of the electrons in the atom have been accounted for. Number 4, an orbital diagram uses arrows to represent the spin of an electron. That is true. Orbital diagrams are when we use the boxes, and then we put arrows to represent the direction the electron is spinning. Remember, if the arrow points up, that's a clockwise spinning electron, and if the arrow points down, that's a counterclockwise spinning electron. Number 5 was false. The ground state, it says here, is the least stable energy state of an atom. Well, that's actually false. The ground state is the most stable energy state of the atom. That's when they're grounded. Well grounded is good, right? So it wants to be stable. Atoms want to be stable. And when the electrons are in their ground state, that is when they are most stable. Number 6, according to Hund's rule, electrons occupy equal energy orbitals so that the maximum number of unpaired electrons result. That is true. When you're filling the electrons into the orbitals, you do fill them so that the maximum is unpaired. So like that's why we don't go up, down, up, down, up, down. We go up, up, up. And then when they absolutely have to pair up, have to, that's when the husbands come home, remember, down, down, down. So that's a true statement. Now, for the next section, you were writing electron configurations. So on the first 3, 7, 8, 9, you were doing longhand, and on the last 3, 10 through 12, you were doing shorthand. So please correct your papers if you missed any of these. And remember, you can always check your electron configurations by adding up the superscripts, and they should add up to the atomic number of the element. So I did that here also, just to verify. So for magnesium, you should have gotten 1s2, 2s2, 2p6, 3s2. For oxygen, 1s2, 2s2, 2p4. For aluminum, 1s2, 2s2, 2p6, 3s2, and 3p1. For 10 through 12, we're doing shorthand. So for argon, you still have to go to the period above the element. Even though argon's a noble gas, don't get lazy, y'all. The rule says you find the element on the table, you go to the period above it, and then you put that noble gas in square brackets. So if you're doing argon, you have to go to the period above him and put the neon in square brackets, because one of the things that you have to do with electron configurations is you have to make sure that you do show the valence electrons. So you'll put neon in square brackets, and then from there you would finish off, you would say 3s2, 3p6. To check your shorthand, remember neon has 10 electrons, and then you add the 2 plus the 6, that gives you 18 total, which is argon's atomic number. Number 11 was argon in square brackets, 4s2, 3d1. Number 12, neon in brackets, 3s2, 3p3. Moving on to the next part, 13 through 17. Remember, the best way, the absolute best way that you want to check your electron configuration to identify your element is to add up all of the superscripts because they're going to equal to the atomic number. Remember, you can have exceptions and you can also have excited states. So you want to make sure that you're very careful with that. If you add up your electrons on 13, there were 20 electrons, so that was calcium. 14 was silicon. 15 was vanadium. 16 would be bromine. And then 17 is neon. Now on 18, it wanted you to address the Aufbau principle, the Pauli's exclusion principle, and Hund's rule. And I think I put these in a little different order than I did on the sheet that I posted for y'all. So just make sure that you are correcting the right rule, because you need to make sure you remember what the rule says. The Aufbau principle is telling us how to build our electron configurations. So you have to fill your lowest energy level orbitals up first. So the 1s has to be filled up before the 2s, and then once the 2s is full, you can fill up the 2p, then the 3s, and then the 3p, and so on and so forth. Pauli's exclusion principle said that no two electrons can have the same four quantum numbers. So that's the reason when the electrons are filling their orbitals, they have to pair up when they pair up with opposite spin. So the wives come home before the husbands. That makes them pair up with opposite spins. You're never going to have two wives in the same box and two husbands in the same box. Remember that. It's always wives, then husbands. Hund's rule says that electrons will fill their subshells or their boxes separately before they pair up. Okay, again, make sure that you have edited your paper if you missed any of those so that you can put those in your exit ticket for today. Now, for the 5-5 practice problems worksheet, I'm going to first go over with you the even numbered problems. Then we'll go over the odds. So, for number 2, you should have said nitrogen because there were 7 electrons there. For number 4, phosphorus because there's 15 electrons there. For number 6, scandium because 21 electrons if you add those up. For number 8, cadmium because there's 48 electrons. And then for the number 10, osmium because there were 76 total electrons. Remember, when you're trying to identify your element from the electron configuration, you add up the superscripts. Whatever they add up to, those are the total electrons in the atom. Since the protons equal electrons in an atom, that is also equal to the atomic number. So you find the atomic number that matches that number of electrons on the periodic table. All right, now let's take a look at the odd numbered questions. Now the reason I'm doing these a little different or separately is because of what the question asked. So let's look at number 1, A and B. Now I did write out the shorthand electron configuration. You could have done either, but this did not specify. So to answer the question that they wanted, how many unpaired electrons does each possess? If you do the shorthand, you're going to be able to tell how many unpaired they possess. You could also tell that from the longhand, but the shorthand is sufficient. So for potassium's electron configuration, you should have argon in brackets 4s1. When you get ready to determine how many unpaired electrons the element has, what you want to do is go to the end of your electron configuration and draw your orbital boxes. Then, so what I did here is I drew one box because it was the s orbital. And then it says that's the 4s1, which means it has one electron in the orbital. So I put one electron in it. And now based on what I see there, there's one unpaired electron. For B, cobalt would be argon in square brackets, 4s2, 3d7. So if you draw the s orbital here, one box for the s, and there's 2 electrons in it, so up, down. And then for the d orbital, there's 7 subshells. So, I'm sorry, 5 subshells, and there's 7 electrons in it. So you draw your 5 boxes, and then you place your 7 electrons in those boxes. So you're going to go wife, 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 husband, husband. That's 1, 2, 3, 4, 5, 6, 7. I put 7 electrons in. So now, based on what we see, there are 1, 2, 3 electrons that are unpaired. Now, anytime you have unpaired electrons, that is going to lend towards being a magnetic substance. So we're not going to have to get into magnetism here, but it could determine if it was diamagnetic or paramagnetic or ferromagnetic, okay? So there are 3 unpaired electrons. Let's look at number 7. 7. So this wanted you to write the electron configurations for bismuth and vanadium, and again, I did shorthand. So for bismuth, you should have xenon in brackets, 6s2, 4f14, 5d10, 6p3. Now, when we write the electron configurations out, notice the s orbital is full, all paired up. The f orbital is full because we are following the Aufbau principle. They're all paired up. And once they're full, we go to the next orbital. The d orbital, there's 10 there. Well, that's the most that the d orbital can hold. So these are all full as well. And so the only place you're going to have unpaired electrons, class, is going to be in the last part of your configuration, if there's ever any unpaired. So with the 6p3, you draw your 3 boxes for the p orbital, and you put 1, 2, 3 electrons in there. So up, up, up. And if you look at what we've drawn, we have 3 unpaired electrons. 3 unpaired electrons. For 7b, vanadium will be argon in brackets, 4s2, 3d3. The s2 is full. The d orbital, you have 5 subshells or 5 boxes, and you're going to put 3 electrons in there. So up, up, up. So literally what you see is 3 unpaired electrons. Since those 2 boxes are empty, you cannot comment on those. When you're trying to determine unpaired electrons, you always go by what you see. What you see is what you get. We have 3 unpaired electrons in vanadium. All right, let's look at number 3. You would have for number 3, silicon is neon in square brackets, 3s2, 3p2, and you should say you have 2 unpaired electrons there. For lithium, helium in brackets, 4s1. If you draw your s orbital and put 1 electron in it, there's 1 unpaired electron in number 3. For number 9, sulfur is neon in brackets, 3s2, 3p4, and again, following the Aufbau principle and Hund's rule, the s orbital is full, so they're all paired up here, but in your p orbital, they're not all paired up, so when you put your 4 electrons in there, you go up, 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 down. You see there's 2 unpaired electrons here. For number 9, you got mercury, so xenon in brackets, 6s2, 4f14, 5d10, and when you look at this one, the s orbital is full. The f orbital is completely full. The d orbital is completely full. That means everybody's paired up. All husbands and wives are home together, so there's 0 unpaired electrons. Number 5, iridium IR. Xenon in brackets, 6s2, 4f14, 5d7. Again, if you look at your orbital notation, they're full. They're full. This one's not completely filled. So you're going to look and see how many unpaired electrons you see there is 1, 2, 3. You have 3 unpaired electrons. For selenium, argon in brackets, 4s2, 3d10, and 4p4. Again, the last part of the configuration is where there's any that are unpaired. There's only 2 that are unpaired here. Now, if I went a little too fast for you on any of those, just pause the video and back it up and rewatch the explanation. But please make sure that you edit your papers for the exit ticket. Finally, the last part of your homework was the electron configuration quantum numbers review number 2 worksheet. So let's look at that. I'll zoom in on it for you. So in number 1, I wanted you to write the longhand electron configuration. For scandium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d1. For francium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s1. Americium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 6d1, and 5f6. That's 7s2, 6d1, 5f6. Now for the next little section, I wanted you to do the shorthand electron configuration. So for bismuth, xenon in brackets, 6s2, 4f14, 5d10, 6p3. For krypton, you would put argon in brackets, 4s2, 3d10, 4p6. And for copper, remember copper is one of the exceptions. Copper and chromium are the two exceptions to the octet rule. There are two exceptions to the electron configurations. So you would put argon in brackets, 4s1, 3d10. This gives you a half-filled s orbital and a completely filled d orbital, which makes the whole atom more stable. Remember, copper and chromium are the two exceptions to your electron configurations. For number 3, we were looking for quantum numbers. So for scandium, and these are all in order, N, L, M, and S. You should have gotten 3, 2, -2, +1/2. For francium, 700, +1/2. For americium, 532, +1/2. For bismuth, 611, +1/2. Number 4, I wanted you to identify the element. So on 4A, I gave you the quantum numbers N, L, M, and S. You should have said that was terbium. For 4B, technetium, Tc. For C, you add up your superscripts, you get 32 electrons, so that is germanium. And for D, that would be rhenium, Re. If you add up those electrons there, you have 75 total, because the xenon has a total of 54, and then you're going to add the rest of the superscripts, 14 plus 2 plus 5. So those are the answers to the homework. Make sure that you correct your papers, and then that will go in your exit ticket.